So good morning, and thank you for attending my talk. Today I'm going to be talking about how lower heat input welding process affects segregation in dissimilar metal weld overlays near the fusion boundary and decreases susceptibility to solidification cracking. This is kind of a revised title from what's in the program, but you'll see later why this deserves its merit. I'm sorry, I'm not on the right slide. Anyway, here's the more appropriate title. I'd like to start out by thanking our numerous sponsors: Arriva, WSI, Babcock Wilcox Canada, Voestalpine, EPRI, ESI, and Fronius. And I'd also like to point out personally Paul Carpenter at Washington University St. Louis for his expertise in electron probe. The objective of this project and presentation is to provide metallurgical understanding for why diluted 52M is susceptible to solidification cracking, or rather why it's really not supposed to be diluted with 304L, and show and explain experimentally why a lower heat input process can reduce its cracking susceptibility. And here's a really nice macro section of a three-layer overlay, multi-bead overlay of 52M on 304L made with CMT. Please point out that there are no lack of fusions like people are often afraid of with the CMT process, although these are very far away from the application conditions, which are highly restrained. So here's some here's the outline of events that I'm going to go over today. I'm going to talk about structural weld overlays and pressurized water nuclear reactors, and then give you just a very cursory overview of solidification cracking in the 52M 304L diluted system, and then talk briefly about CMT and why it's supposedly good as a low heat input process. The experimental results consist of thermocalc analysis, and then EDS and electron probe analysis of the transition zone in these welds. And then I'll conclude with some concluding remarks and future works. So the background for this project is in the nuclear industry. There's a weld geometry called the safe end weld, and it consists of a low alloy steel nozzle coming off of the pressurized water reactor welded to a stainless steel bend or elbow. And this consists of many parts, but what I'm focused on today is the stainless steel side of the weld. What's going on in this weld is 30, 40 years after construction, the utilities have noticed stress corrosion cracking coming off of the stainless part of the weld. And as we all know, stress corrosion cracking, especially in primary water, is bad. We don't want this at all. So as a hedge against this, the utility and numerous support companies have created this structural weld overlay, which is, number one, a corrosion-resistant overlay and a secondary pressure barrier to cracks that might, hopefully not, but might and will breach the surface of the pipe. Here's a list of candidate materials for the structural weld, but today we're going to be talking about the 52M, and I'd like to point out that 52M is nominally a 30 chrome alloy, so it's very stress corrosion cracking resistant alloy, and it's also composed of 8% iron and a little bit of niobium and mostly nickel. So it's a solid solution strengthened, corrosion-resistant nickel-based alloy. Well, what happens when they overlay these pipes with 52M with their standard TIG process, cold wire and hot wire TIG process, is over a certain dilution threshold, the utilities have noticed solidification cracking going on after the weld. And cracks are bad, so we want to minimize the cracking response. EPRI put out this information a few years ago, basically correlating the power ratio which is, my equation didn't get copied down correctly, but power ratio is arc power versus over deposition area, or rather arc energy by deposition volume. So it's a metric by which we can quantify how much power we're putting into the weld. EPRI a few years back correlated the arc power ratio with increasing dilution, and that only makes sense. The more power you put into your weld, the more of the base metal you melt, and therefore you get a higher dilution. And what they notice is above 45% dilution level, they see significant solidification cracking, and below this level, they do not. So what we're trying to target is a bulk dilution level that is below 45% dilution, or rather below 35% weight percent iron, because both of these alloy systems have iron in them. I'll go a little bit into solidification cracking science right now. As we should know, as a metal solidifies from liquidus to solidus, there's a initial planar front that very quickly breaks down to minimize this energy quickly into cellular and dendritic microstructures. And while it's doing that, it partitions low solubility elements to the boundaries between these dendrites. And oftentimes, under the right conditions, it culminates into a solidification crack, or the low melting point liquid is pushed to the boundaries between the solidifying grains. And under restraint, these liquid films can create a very low strength condition where the boundary separates. And this is the basic underlying theory behind solidification cracking, where these interconnected liquid films exist at a very low volume percent at the end of solidification, but still affect the strength, where the material basically has zero ductility. And these factors are greatly exaggerated. This phenomenon is exaggerated by restraint. If the structure is larger at the end of solidification than it should be, it'll crack. The magnitude of the solidification temperature range, and the fraction of low melting point eutectic at the end of our solidification. And this is all exacerbated by the non-equilibrium conditions of welding. Now I'll briefly overview the cold metal transfer process. Cold metal transfer is a little bit of a misnomer. It is actually still hot liquid metal being deposited on but the reason it's cold is because it operates in a space in the potential versus current space that is much lower than these competing low heat input processes. Cold metal transfer is a gas metal arc welding process, a GMAW process, that operates between spray and dip transfer. And the stable droplet transfer is achieved by synergic control of the waveform. And the low heat input is also achieved by the synergic power source detecting when the wire short circuits the base plate, and simultaneously controlling current so it does not so I squared R heating does not contribute to heat input. So what are the effects of this? Well, if I overlay some points that we got from a CMT design of experiment from a related study on the EPRI diagram that I showed before, we see that CMT welds operate in a space much, much lower than the general trend for GTAW. That is to say, there's no strong correlation between power ratio and dilution for CMT like there is for TIG. Therefore, we can achieve, even at extremely high, relatively high power ratios, very low dilution levels, and only in one case did we get this point right here isn't even CMT, so only in one case did we get a CMT weld that broke even 25% dilution, which is still below this 45% cracking threshold. I'd also like to point out that this macro on the bottom here is a cross-section of a weld that was optimized in the mentioned previous study, and it's around 8% average dilution, which is indeed very low and an acceptable and desired level of dilution. So I'll go into the discussion of the presentation then. So what we're talking about when we're overlaying these materials on the 304L base plate is we're depositing liquid filler metal. In this micrograph, it's actually filler metal 82, but it serves the same purpose to demonstrate what we're doing with 52. We're overlaying the 304L base plate with a liquid filler metal with the arc welding process. So we have a filler metal on the top that's transitioning between the filler metal and base metal composition. And we have the liquid metal growing off of the 304L substrate. I'll go into this later, but what's really important in this presentation is this transition is very, very narrow when we're using CMT. And so we can't really compare TIG dilution meaning to CMT dilution, because TIG creates a bead that's more or less pretty homogeneous over the entire bead height or area, whereas CMT creates a very narrow transition zone, so we reach nominal filler metal composition very quickly over a very short distance, and I'll go over those distances later. So what this actually means is as we're solidifying, as we're growing filler metal off of the base plate, we have a transition zone that's spanning on the left here 100% dilution to 0% dilution in a very short amount of time. So it goes through this solidification scheme where blue represents ferritic FA solidification mode, and orange represents A or AF solidification mode. And we have the nickel, chromium, iron eutectic existing in this dashed region. And I've highlighted in red our suspected solidification cracking culprit, niobium carbide matrix eutectic. This is by the way, a Scheil thermocalc simulation of the 304L and 52M system. And at dilutions from 0 to about 60%, thermocalc picked out a second FCC phase, which ended up being, knowing from previous experience, the niobium carbide matrix eutectic. Yes. Also some data from thermocalc. I've plotted the partitioning coefficient K versus dilution starting from 0% on the right. And I've also plotted fraction eutectic. And what this shows us is niobium is relatively soluble in the 52M system. That is to say, 52M as an alloy system can accommodate niobium in the matrix. However, dilutions approaching the 304L composition, even at very low dilutions, cannot accommodate niobium. And the eutectic forms at higher phase fractions, even though the 304L system has much, much lower niobium in it. Going by the EPMA results, this niobium level in 304 is on the order of 0.02 weight percent. So even though 304L, approaching 100 over here, has much, much lower niobium than 52M does, it still can't handle niobium in the matrix, and therefore it partitions more niobium, as evident in this more extreme K value. And so the fraction eutectic goes up as dilution increases. This brings us to the actual experiment that I ran. What I did was I used our previous experiments with the design of experiment to target some specific dilution ranges. So I created a CMT sample with very low dilution, around 1.5% geometric dilution. CMT sample with relatively high dilution, 13.3% average dilution is pretty high for a CMT sample. And I made a TIG weld that ended up being around 30% average dilution. And I zapped these with an EDS line scan traversing the fusion boundary from the base metal all the way into a certain distance into the fusion boundary. And we got some composition data. And I've boiled all this composition data down to a term that I like to call local dilution. This is the dilution that we see at any given point along the line based on the iron content. And I chose iron content because it's the element that varies most between the 52M and 304 composition. So just for example, if we're at some iron value, it'll give us a local dilution value that we can then plot against distance in the scan. So what does this tell us? So looking at the black line right now, which corresponds to the TIG weld, as the traverse progresses, the solidification, the planar solidification front breaks down at about 62% local dilution, leaving that entire 62% dilution left to go during the solidification path. Compare that to the two CMT welds. In these welds, these planar regions break down at 27 and 28% local dilution, leaving a very minimal amount of diluted filler metal left to go in subsequent regions that experience segregation. That is to say, there's a large amount of undiluted filler metal left to go in these CMT samples, compared with a very large amount of diluted filler metal left to solidify in the TIG weld. So what does this mean? Well, looking at the TIG weld solidification morphology, overlaying this up on the Scheil solidification diagram, the planar front breaks down at about 62% as our metal is solidifying from the base metal. And then once that breaks down, it leaves columnar and dendritic and et cetera microstructures that exhibit a lot of segregation to be solidified within this solidification cracking threshold that EPRI has determined. So what's happening in a TIG weld is we're kind of seeing a perfect storm of high solidification temperature range and susceptible microstructure over a range at which we're concerned about solidification cracking. Compare that to, oh yes, I'd also like to point out that the GTA weld bead is so highly diluted that the weld nugget never even reaches 20% average dilution even at the top of the weld. And just for a little context, this planar region that we measured is around 15 micrometers wide, leaving the rest of the about 2 millimeter bead to be highly diluted in a report about segregation. Compare these findings to what we found in the solidification morphology of a CMT weld. The planar solidification region covers a much wider range of dilution that we've observed. So it even encompasses this, this cracking threshold that EPRI had pointed out, leaving this amount on the dilution scale of filler metal to exhibit the subsequent columnar and dendritic solidification, which exhibits our supposed deleterious segregation. And just for some reference here, these planar fronts that we measured were between 7 and 10 micrometers during the study, leaving the remainder of the very minimally diluted filler metal to solidify in this dilution range. Going to some EPMA results. Here's some really good backscatter images of the CMT weld and the GTA weld. What we have going on here is 304L base and diluted, or rather minimally diluted on the CMT side, filler metal on the top. From the results in this experiment and previous experience, we know that these white regions that are perpendicular to the fusion boundary are interdendritic niobium carbide matrix eutectic, and the black dots are titanium carbide particles. And the red circles are the locations of the electron probe traverse. So what we see in the CMT weld is, there is some segregation of our supposed bad actor niobium going on, but it's on a scale that is pretty close to the nominal niobium level, which is about 0.8 weight% in the undiluted filler metal. And as we're approaching the fusion boundary, there's really no scatter in this data, partially because we have a finer microstructure in these CMT welds, and there's very little niobium to begin with approaching 304L composition. And here's some data of all the elements that we considered while we were taking EPMA. It is important to note that as we have spikes in the minor alloying elements that I've listed on the right-hand diagrams. As we get spikes in those, we have minor dips in the major alloying additions that I've shown on the right. But when we compare these data to the EPMA of a GTA weld, we see more or less massive segregation going on between dendrites in this weld, and it's really important to note that this segregation is happening at a pretty high level in a range that's approaching this supposed solidification cracking threshold. So, like I said, it's a perfect storm of all these factors that influence solidification cracking coming together in this region that we're worried about. And as previously mentioned, as we see spikes in these niobium, we see dips in the iron. That's more or less because, looking at the phase diagrams, niobium does not like to be in an iron system. The matrix just can't accommodate this amount of niobium. So this brings us to the conclusions. According to the EPMA, the primary dendrite arm spacing near the fusion boundary is smaller in CMT welds, and there's therefore less evidence of niobium segregation in CMT welds compared to GTA welds. The thermocalc data shows a widening solidification temperature range, and more extreme, i.e. lower K values based on dilution, can partially explain the solidification cracking threshold. Going to the EDS conclusions, the transition zones of a CMT weld are much smaller than GTA welds, leaving a large volume of minimally diluted filler metal left to solidify in CMT welds. And local dilution at the end of planar solidification regions in CMT welds is much lower than in GTA welds. This means that the critical dilution, local dilution level, 45%, is encompassed in a planar region which we're not worried about segregation going on, because by definition in a planar growth region there's no segregation going on. Therefore the planar region encompasses this local dilution threshold, and we're really not worried about cracking because it got rid of the problem. This happens in the CMT welds, but the heat input of the GTA weld prevents this from occurring in that process. Some future work in this project includes smaller scale characterization of the CMT weld microstructure. In order to really get into those dendrite cores and interdendritic regions, we might need some finer scale characterization like TEM EDS, focus beam. We are also doing weldability testing in the cast pin tear test at local dilution levels of 10%, which are characteristic of CMT welds, and of 30 or 40%, which are characteristic of GTA welds. We're also doing analysis of a large CMT overlay that we made in-house with phased array ultrasonic testing, macro section optical microscopy, and guided side bend mechanical tests. So with that, I'll open the floor to questions. This should not say MS&T. Thank you very much.